Here's another Newton's law with friction problem. In this case, let's put a box on a hill and let's slide it down. Let's make this a 30-degree hill and let's put our box up here and it's going to slide down the hill. What I'm interested in this time is, let's say that this has 10 meters to travel down the hill, and somehow, I don't know how, but somehow down here there's sort of this perfectly bouncy object. All right, so what's going to happen is our box is going to travel down the hill 10 meters and it's going to bounce off of this and go back up. What I want to know is, how far back up does that travel? Does it go all the way up 10 meters? Does it go down? Does it go less than 10 meters if this is perfectly bouncy? All right. So things that we know this 30 degrees. Let's say that the coefficient of friction is, let's say like 0.1. And let's say that we're starting with an initial velocity of 0. So we're going to start from rest. It's going to start sliding down. It's going to bounce perfectly, not going to lose any energy or anything, and then it's going to bounce back up. What happens? How far does it go? Does it go 10 meters? Does it go farther than 10 meters, less than 10 meters? What do we know? All right, so that's going to be our problem. First step, coordinate system. We think the thing's going to move in this direction, x and y, so we'll put our coordinate system to look like that. We'll put our free body diagram over here. We know that there's going to be an mg. We know that there's going to be a normal force. And in this case, since the thing is sliding down, so while we're on the way down, we know that friction is going to oppose motion. So force of friction goes that way. And our coordinate system looks like this, x and y. So we have a coordinate system there. Clearly this mg doesn't work for us, so I've got to figure out what, it's not, force of friction is in the x direction, force of normal is in the y direction, mg is in neither. So I'm going to break it up into a y component and an x component, which means that this angle right here is 30 degrees, and I end up with mg sine 30 and mg cosine 30 up here. Okay, so there's my free body diagram. I can write down some of the forces in the x direction, some of the forces in the y direction. X direction, I have an mg sine 30, and I have minus force of friction. That's it, equals mass times acceleration in the x direction. In the y direction, I have an F normal, and I've got a minus mg cosine 30, and that's going to equal mass times acceleration in the y direction. So there's my two equations. Notice that I didn't give us any mass. I don't know the mass. The mass is not something that I know, so I just have to carry these m terms around until hopefully they cancel out or it becomes unnecessary for us to know. Alright, so again, this is sliding. We chose our coordinate system wisely. This is sliding in the x direction only, so my y acceleration is 0, which means that my normal force is equal to mg cosine 30. And since I don't know the mass, that's all I can do right now. I do remember that force of friction is equal to mu F normal, so I can make that substitution. Right? I know the force of friction, I know F normal, so I can take this guy and say mg sine 30 minus mu F normal equals max, or mg sine 30 minus mu F normal is equal to mg cosine 30 equals max. And here I finally notice there's an m in each term, so I can reduce those out, and I find that the acceleration in the x direction is equal to g sine 30 minus mu g cosine 30, and those are all numbers. I know g, I know sine 30, mu g cosine 30, so I find out that the acceleration in the x direction is Let's plug that in. 9.8 sine 30 minus 0.1 times 9.8 times cosine 30, and I get an acceleration of 4.05 meters per second squared. So there's a nice acceleration. That's for my trip down, and I can now I guess figure out what my velocity is here. I know the distance, so I can find my velocity and see what happens. So I know v0, v, a, t, delta x, initial velocity is 0, acceleration 4.05, delta x is equal to 10 meters per second squared. I'm looking for final velocity, so I could say v squared equals v0 squared plus 2a delta x. So that's going to equal to 2 times 4.05 times 10. So v is equal to square root. Final velocity is going to equal to plus or minus 9.00 meters per second. Okay? I'm going to probably choose the plus because down is plus, so we'll put in plus 9 meters per second. Okay? So that's all for the trip down. Right? I found, and if I wanted to find time I could. I'm not sure if I'll need that, but I'll leave it for now. So on the way down I started with initial velocity of 0. I accelerated at 4.05 meters per second squared, and I ended up with a velocity of 9 meters per second down. What about on the way up? Since it's perfectly bouncy, v0, v, a, t, delta x, I know that my initial velocity on the way up will be negative 9 meters per second. I know that my final velocity will be 0 because I want to figure out how far does it go before it stops. And I'm looking for delta x, so I guess I need to find the acceleration. The question is, will the acceleration be the same as this? Well, let's do a free body diagram and figure it out. If I do my free body diagram for the way up, I still have F normal, I still have mg, but since the box is moving up, now force of friction is moving down. It's opposing motion. So I have different equations, and I'm going to keep my same coordinate system because I chose here, so I'm going to have x and y. So what happens here, sum of the forces in the x direction, what do we get? In the x direction, now we get force of friction, and we get plus this same mg sine 30 equals mass times acceleration in the x direction, and some of the forces in the y, we get force normal minus mg cosine 30 equals mass times acceleration in the y. Once again, acceleration in the y is 0, so F normal equals mg cosine 30. We notice that nothing changed in the y direction. But in the x direction, instead of minus force of friction like I had up here, I get positive force of friction like I have here because the box changed directions, so friction also changed directions. What that means is, again, I can do force of friction as mu F normal, so I can take this guy and say mu F normal, so mu mg cosine 30 plus mg sine 30 equals mass times acceleration in the x direction. All of my m's still go away, and I'm going to get the acceleration in the x direction is, this time, g sine 30 plus mu g cosine 30. So in this case, the acceleration is going to be, let's see, 9.8 sine 30 plus 0.1 times 9.8 times cosine 30. We're going to get the acceleration of 5.75 meters per second squared. So the acceleration is bigger in the positive direction. So the accelerations are not the same. I have to go back up here then. Plug that in. Acceleration is 5.75 meters per second squared. Positive acceleration, but because I'm traveling in the negative direction, I'm still slowing down. And I can do a calculation using v squared equals v0 squared plus 2a delta x, or delta x is equal to v squared minus v0 squared over 2a, which means 0 minus 9 squared over 2 times 5.75, or 81 divided by 2 divided by 5.75, and I get delta x equals negative 7.04 meters. So in this case, we find out we started up here at 10, went down, bounced, and went back up 7 meters. So it did not go as far as we want, not because we lost any energy here at the bouncy thing, this is perfectly bouncy, but because friction changed directions. Friction slowed us on the way down, and it also slowed us on the way up. So it's another example of how we can use friction, and we just have to be careful that, on the way down, friction's in one direction, on the way up, friction's another direction, and we want to make sure that we're not just making assumptions. We're going to draw a free body diagram for each one.